right, so we're going to end this U substitution section. There's been a lot of videos here. We're going to look at another example and then try to kind of summarize a little bit what we've done here. So number 3, let's take a look at one more example here. Suppose I have the integral of 4 to the negative 1 over x all over 3x squared dx. All right, so I don't see a lot of the usual inside functions that we talk about, things inside of powers. Maybe you're thinking, oh, you should be the denominator. We've done that before, but I hope you're getting to a point where you realize the whole idea of picking u is then that the du, the kind of the derivative, the differential of that is also present in the integral. That's the idea, right? So if I let u equal 3x squared, what's du? 6x dx? That's not what's left. And what about that 4 to the, like, that just doesn't seem right. So you're trying to find a u where when you take that du differential, that is pretty close to the remaining kind of portion in the integral. So I hope you're thinking about, well, when you learn derivatives, for example, inside functions of exponential functions were what was up in that exponent, right? That's the inside of an exponential function. So this is a kind of a new type of inside that we haven't yet done with integrals. Certainly we saw it with derivatives. If the inside of an exponential function was more than just an x, that's when we had to do chain rule. So we're going to let u equal this negative 1 over x, or for purposes of differentiation, negative x to the negative first. So taking our derivative, of course, we have x to the du equals x to the negative second dx. Now, if I had an integral that had a bunch of negative exponents in it, I'd work with that, but I don't. So my first instinct would be to just rewrite this as 1 over x squared dx. And that looks really good because that matches up with the remaining x's and dx's that are in my integral. So in the remaining integral, I have a dx over, or just even think of it as a 1 over x squared dx. And that is exactly what du is equal to. This 3 is just a constant multiple. It's just 3 times x squared in that denominator. So I can even just bring that out as a 1/3 factor. And then all I have is my 4 to the u du. So this looks like a nice little substitution here. So that's my u, and this is my 1 over x squared dx. That's the du right there. All right, so this is good. So hopefully you remember this is one that we know from our list of the original kind of antiderivatives we discussed in 4.8. Look at the very last one here. Your integral of a to the x is a to the x over natural log of a. So let's go back and kind of finish this one out here. So we are going to have, this is going to equal, my 1/3 is going to get carried along here. And so we're going to have our 1/3 integral of 4 to the u is going to be 4 to the u divided by natural log of 4 plus c. You can, certainly you have to replace that with what the original u is. The constant in the denominator, you could leave those like they are. If you wanted to think of 3 times natural log of 4, as being natural log of 4 to the cubed, 4 to the third, or 4 cubed. That is a property of logs, and then 4 cubed would be 64. Now, that's an option. You wouldn't have to. But certainly you need to replace your u with the negative 1 over x. So there's our result. All right, so let's take, I have a little extra space here off to the side. So let's just take a second and kind of summarize a bit and talk about what I'm going to refer to as common choices for u. So there is no always when it comes to u substitution or integration in general. All we can talk about here essentially is going to be things that result frequently. The main big broad idea is you're trying to identify a u whose differential du kind of matches up with what's left in that integral. But we've certainly developed some ideas along the way. So let's just summarize those just for a minute here. So the first one, what's often a choice for you, is if you have a natural log function, natural log, again, of some sort of, there'll be x's on the inside. So I'll say, it could be just natural log of x or 2x minus 1 or whatever it is, anywhere in the integral. So this natural log function could occur, I'll just say, anywhere in that integral, meaning in the numerator, in the denominator, inside of something being raised to a power, or not. So if you remember when we did that example, the whole reason, this is not like, this is the one I'm doing first. It kind of defies our usual, oh, we're looking for an inside function conversation. And the reason is because you don't know a function whose derivative is natural log of x. So we can't ever integrate even just plain old natural log of x, right? That was our conversation when we did an example with that. Even if I just gave you that, you wouldn't know, we don't know a function whose derivative was natural log of x. So that's why if there's a natural log of x in that integral, that's going to be my choice of u because I need to get it out of there. So that's kind of the first one that almost defies the usual approach that we take with these. All right, so the usual approach, kind of where we started with u's, had to do with things that were inside of functions that were being raised to outer powers, right? So again, let's just actually, instead of calling that ... so we're talking about functions that are inside of outer powers, right? So things being raised to the nth power, or things that are inside of radicals. So that's also just, 1 over n power or something like that. So in these situations, our choice for u on these is going to be that the u in these situations is really what is inside of those powers. So for the u, we're talking about things inside of outer powers. So that's probably our most common, that's sort of where we started, letting u equal something that is inside of outer powers. All right, what else did we learn? Kind of an extension, I guess, of that one is, again, so these two, when I'm talking about this, again, these are situations where these may be occurring anywhere, that's an arrow, anywhere in that integral. Like those may be up in numerators or down in denominators, so things inside of outer function, or things inside of outer powers. Okay. But another one that we saw had to do with if we just had maybe some sort of like a numerator function, so kind of anything could be happening in the numerator, and then just a denominator. And maybe that denominator isn't being raised to an outer power, but just this idea of letting u equal the entire denominator. And so we've seen that before. I think I have one real close here. We did that one of those last time. So that's like this one part b up above. So that was a common one that we saw a few times. Okay, another couple of situations happened early on with trig functions, let's say. So when you have maybe sine, let's just say, of a function, or cosine of a function, and so on. So oftentimes, if you have inside functions inside of the trig functions, so those can sometimes be good choices for u's. Let's see, what else? Maybe this last example that we just looked at here. So when we have, let's see, exponential functions, it could have been an e, or in this situation I had some other base. I had a base of 4. But when you have something up in an exponential function that is more than just obviously a plain old x, that is often our choice for u. So like what's up in an exponent, because that's the inside of an exponential function. All right, now the other, I'd say, big topic that we talked about here had to do with those binomials that end up maybe giving us one of those inverse trig results. So for example, let's take a look at like one part A, which ends up repeating itself in one part C there. So a lot of times if you have a binomial that you think you're seeing something that looks similar to a structure, so maybe you have something, let's say, it could be a constant or something, but I'm going to say something over like an a squared plus and maybe some sort of f of x squared, or something else in a denominator that has to do with maybe the subtraction ones that we did. So maybe it's going to be, we ended, well, the one that you're looking at right here last time that ended up being this arcsecant one. It could also be one that results in the, maybe if you have something that looks like an a squared minus f of x squared, maybe under a radical here. Now, often what happens with these is that, I'm going to actually take the 1 off of here, is typically within that integral, you're going to also have f prime somewhere in that integral. But right now I'm just kind of trying to summarize like what are things that you look for your f of x. And so as you look at these, okay, or maybe even, something that's in a denominator with a square root, the two that have to do with the x squared minus a squared or a squared minus x squared, those are the two that are under radicals. So these are often choices for f of x because these might often, if they're in denominators, and for the last two, if they're under radicals, these might give us one of those inverse trig functions as our answers. So those are other things that we've seen. So we have a lot that we've looked at here, but these are some of the, again, integration is an art form, so it's going to take practice. But these are the things that, as of right now, that we've seen and we've sort of built up to. There's probably going to be some other things in your homework. Believe it or not, I could do 5 more videos and still probably not hit everything. I've tried to hit the major things. But there will be ones in homework that we will look at in our Zoom meetings, no doubt. All right, so the last little bit here, actually, we talked about this before. We did this back in a previous section, and in fact, I took a picture of that so I could have that here. So yeah, this was on page 14. So for these, I'm just going to say, because I kind of already introduced that, I'll just say see page 14. I don't know what video that was, but here's where we talked about, I did an example of this before. So when you have an even function, because of the symmetry, you can just take 2 times the definite integral from 0 to a. If you have an odd function or something with that origin symmetry, those 2 areas would be equal in area. So when you take your definite integral, because the area below the x-axis results in a negative definite integral, that comes out to be 0. So you can go ahead and kind of take a look back on page 14, and we already did a couple of examples of those. So I'm not going to go through those again. So this is the last video. You made it, woohoo, in our Calc 1 series here. But still more to do with these U subs. So I'll see you in Zoom meetings, and I have no doubt that you'll give me plenty of questions to be able to fill up our class time as we continue to look at more examples.